Welcome to Copilot Podcasts. The universe didn't begin with a big bang. It emerged from a geometric saddle point where space-time curvature changes sign. Today, we're diving into saddle point cosmology, a radical new framework where matter is literally refined geometry, where the cosmos evolves through infinite cycles, and where a mysterious observer called the Penrose eye selects which reality we experience. By the end of this episode, you'll understand how curvature flows create galaxies and why deep field telescopes are seeing structures that shouldn't exist yet. So let me get this straight. We're talking about a completely different origin story for the universe?
Exactly. Instead of starting from a singularity, the universe emerges from what's called a mixed curvature saddle point on a vacuum manifold. Think of it like a mountain pass. You have positive curvature on one side, negative on the other, and right at the saddle point, small perturbations can grow rapidly.
Wait, what's a vacuum manifold? That sounds pretty abstract.
It's basically the geometric structure of empty space itself. The page content describes it as a smooth manifold V equipped with a vacuum potential U that maps every point to a real number. Different regions have positive, zero, or negative curvature.
So space-time itself has this underlying geometric structure even when it's empty?
Right. And the critical insight is that saddle points, where the gradient of this potential is zero, are where interesting things happen. The research defines critical points as places where the gradient VU equals zero, and saddle points have what's called a Morse index between 0 and an.
Morse index, that's measuring something about the curvature?
Exactly. It counts the number of negative eigenvalues of the Hessian matrix at that point. So a saddle point has some directions where curvature curves up and others where it curves down. It's unstable, like balancing on a mountain pass.
And somehow this instability creates matter?
This is where it gets really wild. The paper describes something called the AGG operator, a topological index refinement operator that gets triggered by what they call a 4-mo jolt. This is a quantized curvature excitation of magnitude 4 mo applied to a spherical patch.
4 jolt? That's oddly specific.
The 4 mo factor keeps appearing in physics. It's the surface area of a unit sphere, the solid angle around a point. Here it seems to be the critical threshold for destabilizing a saddle point. The equation shows K of the saddle point plus AAK equals 0.
So what happens when this AGG operator fires?
The saddle point gets refined into 3 critical points. The paper shows AGG maps one saddle point to 3 points labeled PPP, PE, and PO. And here's the kicker. These correspond to a proton, electron, and neutrino.
Wait, you're saying fundamental particles are just geometry?
According to this model, yes. The proton corresponds to positive curvature, the electron to flat curvature, and the neutrino to negative curvature. Matter is literally a geometric refinement of curvature. The paper states, matter is thus a geometric refinement of curvature.
That's completely different from how we usually think about particles.
Right. And there's this conservation law, the Morse index of the original saddle point equals the sum of the indices of the 3 refined points. So the total topological charge is preserved during matter creation.
But how do we get from this geometric picture to the universe we actually observe?
This is where the observer comes in. The paper introduces something called the Penrose eye, an observer positioned not within the curvature manifold, but at its conformal boundary. It's like being at the point north of the North Pole on a sphere.
The Penrose eye? That sounds almost mystical.
It's actually a precise mathematical concept. The page content describes it as occupying conformal infinity where hyperbolic and spherical sheets collapse into a single topological map. From this perspective, the observer perceives the entire saddle transition as a unified global structure.
So this observer is somehow outside normal spacetime?
Exactly. It's positioned at the conformal boundary, similar to how Penrose-Carter diagrams work in general relativity. The research states that because spatial and temporal distances are conformally compressed at this boundary, the eye perceives curvature sign, AGG refinement, and the 4-mo jolt within a single coherent frame.
And this observer somehow selects which reality we experience?
Yes, through what's called the observer operator. There's a phase field OP that maps the vacuum to the circle S1, and the observer operator O mod P selects a single phase coherent branch. This selection defines the arrow of time and the realized cosmological history.
So the direction of time itself emerges from this geometric selection process?
That's what the model suggests. Once the observer selects a branch, the eon evolves according to a gradient flow equation, dx dt was ux. Curvature flows away from the saddle into attractor basins.
And these attractor basins become...
Galaxies, clusters, the cosmic web. The paper states that attractors correspond to stable curvature minima, and basins of attraction form galaxies, clusters, and the cosmic web. It's like water flowing downhill, but with curvature instead of water.
What about dark matter halos? How do they fit into this picture?
This is really interesting. The model treats dark matter halos as boundary layers rather than particle halos. Halo boundaries occur at curvature thresholds where kx equals k crypt. They're geometric surfaces, not collections of particles.
So dark matter isn't actually matter at all?
In this framework, it's a geometric effect, sharp transitions in the curvature field that we interpret as gravitational boundaries. The 4μ factor keeps appearing in physics, from the surface area of spheres to solid angles, and here it's showing up in curvature transitions, which suggests some deep geometric principle.
But what happens when this eon ends? Does the universe just stop?
No, this is where the multi-eon topology comes in. As curvature dissipates, the manifold approaches a new global saddle, preparing for the next 4μ jolt. The research describes a bi-infinite chain of vacuum manifolds, each equipped with a mixed curvature potential.
So the universe is cyclical? Like an infinite series of cosmic epochs?
Exactly. The multi-eon manifold M is defined as the union of all these vacuum manifolds Vk, where k ranges over all integers. Eons are glued together at their saddle boundaries. EVK is topologically identified with AVEK plus 1 OB.
And this preserves some kind of topological structure across cycles?
Yes, the Euler characteristic is preserved. Each compactified manifold has Euler characteristic EE(2), and the entire chain inherits a global Euler characteristic of 2 when viewed from the ultimate conformal boundary. No topological defects accumulate across eons.
The universe doesn't have a beginning or end. It's an infinite chain of eons, each starting from a geometric saddle point and flowing back to create the next cycle. That's a completely different way of thinking about cosmic time.
And there's this beautiful entropy conservation principle. The paper describes sink entropy conservation, where the Penrose eye acts as a global sink where all residue mismatch radiation terminates, ensuring total entropy is conserved across the entire system.
So even across infinite cycles, entropy is conserved?
Yes, through what they call the residue invariant, RS, and the Euler crystal invariant. The total entropy, S total, use SSBH plus SRAD plus SI, remains constant. Every residue mismatch quantum from every horizon saddle in every eon reaches the Penrose eye boundary in finite conformal time.
This all sounds very theoretical, but does this model make any testable predictions?
Actually, yes. The paper lists several observational predictions. Deep field surveys should show excess massive galaxies at high redshift, early disks, bars, and rings, and accelerated nonlinear structure formation.
Wait, early overmassive galaxies? Isn't that exactly what JWST has been finding?
That's the connection. The paper states that deep field observations from Hubble, JWST, and Euclid reveal structures that appear too massive, too organized, or too dynamically evolved for their inferred cosmic age. These anomalies motivate the saddle point framework.
So the model was developed to explain observations that don't fit standard cosmology?
Exactly. It also predicts lensing anomalies, asymmetric arcs and rings, non-NFW mass profiles, and coherent residuals in lens reconstructions. Plus, halo edges should appear as sharp geometric layers with universal properties.
And these would all be signatures of the underlying geometric structure?
Right. The model also predicts phase-coherent anisotries. Large-scale structure should retain directional correlations inherited from the saddle escape direction. These aren't random fluctuations, but geometric imprints from the initial saddle point.
The Penrose eye concept reminds me of how we think about black holes. This observer positioned outside normal spacetime, seeing everything from a completely different perspective. It's like the ultimate cosmic vantage point.
That's a great analogy. And just like with black hole horizons, the Penrose eye provides a way to understand global properties that aren't visible from within the system. It's the formal symbolic representation of the global observer in the cosmology.
But how would we actually test whether this geometric picture is correct?
The key would be finding those universal halo boundary signatures and the specific lensing patterns. If dark matter halos are really geometric boundary layers at curvature thresholds, they should have very different properties than particle-based halos.
And the early overmassive galaxies that JWST is finding, those would be natural in this model?
Yes, because structure formation is accelerated by geometric effects rather than just statistical fluctuations. When curvature flows rapidly away from the initial saddle, you get faster collapse and earlier massive structure formation.
It's fascinating how this connects abstract geometry to concrete observations. What would it mean if this model is correct?
It would completely revolutionize our understanding of reality. Matter wouldn't be fundamental, it would be emergent geometry. Time wouldn't be linear, it would be cyclical. And consciousness, through the observer operator, would play a fundamental role in selecting which branch of reality we experience.
That's a pretty radical departure from standard physics.
True, but the paper presents it as a structurally complete alternative to singularity-based cosmology. It offers concrete, testable predictions and addresses anomalies that standard models struggle with. The research concludes that it provides a unified geometric and topological framework for understanding matter creation, cosmic evolution, and deep field anomalies.
So when you step back from all this, we're looking at a model where the universe emerges from pure geometry, evolves through curvature flows, and cycles infinitely through topologically connected eons.
And where an observer at conformal infinity somehow selects which branch of this geometric reality we experience. It's a cosmos where matter, time, and even consciousness emerge from the fundamental structure of curved space-time itself.
The implications are staggering. If this is right, then every particle in your body, every galaxy in the sky, every moment of time, it's all just refined geometry flowing through an infinite chain of cosmic saddle points.
And the next time you look up at the night sky, you might be seeing the geometric shadows of curvature flowing toward the next cosmic transition, the next 4-me jolt that will reshape reality itself.
That brings us to the end of today's Copilot podcasts. Remember, the universe you think you know, built from particles and starting with a Big Bang, might actually be pure geometry in disguise, cycling through infinite eons of curvature and time. Thanks for joining us on this journey to the edge of cosmic possibility.